How does an access and mobility management function, the AMF, find the right unified data management instance when a phone registers on a 5G network? In a cloud of identical looking services, hard coded addresses break the moment you scale or fail over. That is the problem the network repository function solves. The NRF is the live directory of the 5G service based architecture. Network functions announce who they are, what they offer, and how healthy they are. Other functions ask the NRF where to go next. Think of it as a dispatch desk that never sleeps. Every service checks in, and every caller gets a current answer, not a stale phone book. In this lecture, we will walk the full NRF story: profiles, registration, multi region federation, a real UE registration call flow, the NNRF APIs, and why the NRF is mandatory in the SBA. Before anything can be discovered, a network function must register. Registration is the act of publishing an NF profile into the NRF. That profile is not a name tag, it is a living resume. It carries identity, an NF instance identifier, and the NF type: AMF, SMF, UDM, and so on. It carries status, typically registered, plus heartbeat timers so the NRF knows the instance is still alive. It carries reachability, FQDNs, IPv4 addresses, and IP endpoints with ports. It carries capacity, load, and priority so selection can favor a healthy instance. And it carries type-specific information. For an AMF, that means region and set identifiers, GOMAI mists, and tracking area information. For a UDM, it means SUPI ranges and the subscriber data services it exposes. An NRF can also register with other NRFs, and its own profile may summarize NF instances already known to it. When we look at real operator dumps later, you will see exactly these fields filled in: dynamic instance IDs, heartbeats, service names like newdm-sdm, and capacity versus load. The point is simple: registration turns a black box microservice into a selectable, routable peer. Zoom into the type-specific side of the profile, the part that makes selection correct, not just possible. On the source slide, two AMF-oriented examples appear. One path lists AMF identifier, AMF region, and AMF set. Another expands into lists the NRF must store: GWAMI, the globally unique AMF identifier, and TAI, the tracking area identity list that says which radio geography this AMF covers. Why does that matter in the real world? Imagine a phone moving through a city. The core should prefer an AMF that already owns that tracking area and sits in the right region and set, not a random AMF on the other coast. The profile is how the NRF encodes that preference. Capacity and priority then break ties among valid candidates. So when we say discover a suitable AMF or UDM, suitable is not a vibe. It is a match against these typed fields. The same idea applies when an NRF profile carries summaries of instances already registered beneath it. Higher tier NRFs inherit just enough metadata to answer cross-region questions without cloning every raw database row. Registration is half the story. The other half is discovery. Discovery is when a consumer NF asks the NRF, "Give me a suitable producer for this service under these constraints." The NRF looks up matching profiles and returns group identifiers and concrete NF instances the consumer can contact. That is different from registration. Registration is publish. Discovery is query. Status handling sits beside both. Consumers can subscribe to status changes and receive notifications when an instance goes unhealthy or leaves. Here is a concrete picture. An AMF starts UE registration. It does not guess a UDM address. It sends a discovery request with inputs such as SUPI or routing identifiers. The NRF answers with a UDM group identifier and candidate UDM instances. Later, the UDM itself discovers a UDR the same way. Only after discovery does the consumer open a service API toward the chosen instance. So the NRF is the first step of selection, not the session itself, but the map that makes the session possible. One NRF is not enough for a national operator. Take the T-Mobile style deployment shown in the source. There are regional pockets, west for AMF and SMF, south for AMF and SMF, and a central region that holds functions like UDM. Inside each region, local NFs register upward into regional NRFs. Regional NRFs also register to each other, so West can learn about South without hardwiring every pair of boxes. Regional NRFs register into the global or central NRF tier, and central NRFs register to one another for resilience. Picture local city directories connected to a national directory. A clerk in the West can still find a central UDM because the directories are federated. The diagram shows layered NRF nodes, W1, W2, W3 in the West, S1, S2, S3 in the South, C1, C2, and peers in Central, with many thin links between regions. Those links are the Federation fabric. Without them, Discovery stays trapped inside one metro. With them, an AMF in the South can still resolve a UDM living in Central, and the core stays one logical service mesh even when hardware is geographically split. Now the detailed flow. Service registration during UE registration told first in words, then shown step by step. Start. A UE registers and the signal reaches the AMF. Step 1, the AMF discovers toward the NRF. Inputs include SUPI or a routing identifier. Outputs include a UDM group identifier and UDM instances. Step 2, the AMF performs registration toward the UDM it selected. Step 3, the UDM itself discovers through the NRF. Inputs include SUPI or group identifier. Outputs include a UDR group identifier and UDR instances. Step 4, the UDM does get and update against the UDR to read and write subscriber data. Step 5, the AMF creates an SM context toward the SMF, carrying UDM group and routing information so session management stays consistent. Step 6, there is another discovery path involving group and routing identifiers that returns UDM instances when needed higher in the chain. Step 7, registration also runs toward the SMF side of the story so session producers are known. Step 8, further get and update traffic continues between UDM and UDR as the context settles. Notice the pattern. Almost every solid arrow that matters is preceded by a dashed discovery hop through the NRF. Without those hops, AMF, UDM, UDR, and SMF would be guessing endpoints. With them, the registration cascade is dynamic, multi-instance safe, and ready for regional failover. Let us slow the UE registration cascade into a story you can retell on an exam. Act 1 is mobility. The UE hits the AMF. The AMF's first job is not to invent subscriber data, it is to find who owns that subscriber. Discovery 1 toward the NRF uses SUPI or routing identity and returns a UDM group plus instances. Registration 2 binds the AMF conversation to that UDM. Act 2 is data. The UDM is not a dumb file server. It discovers a UDR with SUPI or group identity, then performs get and update to pull and store the subscription record. Act 3 is session. The AMF creates an SM context toward the SMF, carrying the UDM group and routing identifiers so the session path stays consistent with the identity path. Registration 7 toward the SMF, plus further get and update 8 between UDM and UDR, close the loop as the context stabilizes. If you remember only one visual rule from the diagram, remember this. Solid service arrows are almost always preceded by dashed discovery arrows through the NRF. That is the difference between a brittle core and a service-based one. The source also shows real NRF database dumps, yellow configuration panels that prove the directory is operational, not theoretical. On a UDM entry, you see NF type equals UDM, NF status equals registered, a heartbeat timer of 600, create and last heartbeat timestamps, PLMN lists, NSSAI values, and inter-PLMN FQDN, and IPv4 addresses. Under NF services, you see named services, NUDDM-SDM for subscriber data management, NUDDM-UECM for UE context, NUDDM-UEAU for authentication, each with version, HTTP scheme, IP endpoints, capacity 100, and load 50. On an AMF entry, the pattern repeats. NF type AMF, registered status, locality east, AMF info with region identifier, set identifier, and a GUAMI list, plus services such as NAMF-COM and NAMF-EVTs with the same capacity and load fields. These are the knobs selection uses. Capacity and load tell you who can take more traffic. Endpoints tell you where to open HTTP. Status and heartbeats tell you who is still alive. The NRF is storing actionable metadata, not just pretty names. Architecturally, the NRF mainly supports the service discovery function, the first step of selection, and it is a mandatory component of the service-based architecture. The interface is called NNRF. Transport is HTTP over TCP. Serialization is JSON. That matches the rest of the SBA service mesh, clean, web-style APIs between network functions. The NRF API is exposed to the management and control functions through NNRF. Services split into two families. First, NNRF_NF management. NF register to publish a profile, NF update to refresh it, NF deregister to leave cleanly, NF status subscribe and NF status unsubscribe to watch peers, and NF status notify so the NRF can push status changes. Second, NNRF_NF discovery with NF discover, the query that returns matching instances. On the reference architecture diagram, the NRF sits on the service bus beside NEF, PCF, UDM, AUSF, AMF, SMF, and friends, with NNRF drawn as the spoke that ties producers and consumers together. If NNRF is down, registration and discovery freeze, and the SBA loses its ability to find itself. Place the NRF on the full service-based architecture map. On the reference diagram, control plane functions sit on a shared service bus. NEF, NRF, PCF, UDM, AF above, AUSF, AMF, SMF below, the UE and radio access on the left, UPF and data network on the user plane. The NRF is drawn with the NNRF interface hanging off that bus like a labeled spoke. That drawing is not decoration. It says every producer and consumer that wants dynamic peers speaks NNRF for management and discovery before it speaks its own service API. NAMF and SMF and UDM and the rest. HTTP2 over TCP with JSON serialization is the common tongue, so tooling, tracing, and gateways look like modern microservices rather than proprietary telecom stacks. Mandatory means this. If you remove the NRF, you do not merely lose a nice-to-have directory, you remove the first step of selection for the entire SBA. Operators therefore deploy NRF in redundant regional and central tiers, exactly as the T-Mobile style federation showed, so the mesh can still find itself under failure and growth. Pull the thread tight. The NRF is the continuously updated directory of the 5G core. Network functions register rich profiles, identity, type-specific data, endpoints, capacity, load, and status. Consumers discover suitable instances instead of hard-coding peers. NRFs federate across regions so a West AMF can still reach a central UDM. In the UE registration call flow, almost every meaningful hop is preceded by an NNRF discovery. Management APIs keep the directory fresh. NF Discover answers the question, who should I call? HTTP2, TCP, and JSON keep the interface aligned with the rest of the SBA. Remember the dispatch desk. Announce yourself, ask for the right desk, and trust the board to stay current. That is how a distributed 5G core finds itself. Every time a phone